This video is going to cover part 7 of our gas law notes. It's on vapor pressures and the graphs that are associated with them. Vapor pressure is basically the pressure of the gas molecules trying to escape a liquid and become a vapor. For that to occur and for all the liquid to be able to escape, the vapor pressure of that liquid has to equal the atmospheric pressure, and that's when boiling occurs. And so, depending on the temperature you are at, the vapor pressure of that liquid will vary for boiling to occur. There's two different types of liquids we're going to talk about. The first one we're going to look at are non-volatile liquids. These are liquids that do not typically become gases very easily. They have very strong intermolecular forces, the connections that are forming between the molecules that have to be broken. And as a result, they require fairly high boiling points and have lower vapor pressures because most of the energy is placed into breaking those connections, the intermolecular forces between the molecules. Examples of non-volatile substances would be water. Volatile substances are the opposite. They do become gases fairly quickly. They tend to boil at much lower temperatures, and that's because they have weaker intermolecular forces. Their connections are not as hard to break. And so they have a little bit higher of a vapor pressure because the energy is put into turning that liquid into a gas rather than breaking the connections between the molecules. Examples of these would be like nail polish remover, alcohols, methanol is one. If you've ever filled your car up during the summer, you've seen vapors coming off of the gas pump as you fill up your car, and that too is an example of a volatile substance. Just to review intermolecular forces, we talked about these back when we talked about changes between solids and liquids and gases. They are not the physical bonds holding the atoms together in the molecule, but they are connections between adjacent molecules. There's different types of intermolecular forces. London dispersions are the weakest. Those are the ones that are more like tape. Dipole-dipole would be more like rubber cement, and then hydrogen bonds would be more like superglue. And hydrogen bonds are the ones you're probably more familiar with from water and biology. They're the ones that hold the bases together in your DNA molecule. Regardless of the type of intermolecular force you have, those have to be broken before a substance can be changed from solid to liquid or liquid to gas. If you have more hydrogen bonds, you're going to require greater inputs of energy for those forces to be broken. So we're just going to go over a couple of questions with this curve. As we talked about, volatile substances tend to have higher vapor pressures, whereas non-volatile have lower. So if we take a temperature, say at 20 degrees, we're going to see that substance D is going to require a lower vapor pressure than substance A. If we pick a pressure, say 60 kPa, and we go across, we will see that substance A will boil at a lower temperature than substance D. These curves are the pressures and temperatures at which these liquids will boil at. That's the minimum pressure you must have at that temperature for a liquid to change to be a gas. So since substance A has a higher vapor pressure and a lower boiling point, it would be the more volatile of the choices we have. So the ones that are closer to the y-axis are volatile, while the ones that are further away, like substance D, are more non-volatile. So if I ask you if substance C is volatile or non-volatile, it would be more non-volatile. If I ask you to find the boiling point of substance B at 40 kPa, we would want to find where that curve intersects at 40 kPa for substance B, and then we would want to extend that line down to our x-axis to determine that temperature. We may not all exactly agree on the temperature, but I would say this one's probably pretty close to 34 degrees Celsius. If I ask you to find the pressure at which a substance boils at a given temperature, this time I'm asking you for substance C at 65 degrees Celsius, I would find 65 on my x-axis, go up to where substance C's curve crosses 65 degrees, and then I would go across to get the pressure. So it looks to be a little below 70, and I said around 65 kPa. You may think a little lower, a little higher. We talked about normal boiling point back with our phase diagrams. Normal is referring to a pressure of 1 atmosphere. Because our graph is in kPas, that's 101.3. So we're going to find that normal pressure where it crosses curve A, and then we will go down to get the temperature. And I said that one was around 34 degrees as well. Again, you might have thought a little bit less or a little more. And the final question, which substance has the weakest intermolecular forces? That's going to be our more volatile substance. So that would be substance A. That's the end of video 6, and at this point, it's pretty short and sweet. You should be able to do the questions involving vapor pressure curves.